the absolute value inequalities, right? Is that what y'all are talking about? I have to think back to what we're doing. So f of x is less than 4x plus 1 minus 3. All right, so I want to set that inside equal to 0. And when I do, I get 4x equals negative 1, so x is negative 1/4. That's the one I'm going up and down from. So negative 1/4, I want to go 2 up and 2 down, and I probably want to stick to nice whole numbers. Okay, so maybe I choose 0 and 1, and then maybe negative 1 and negative 2. It doesn't matter what you pick as long as you're on either side of that value there, that x value. If I plug in negative 1/4, of course this gives me 0, and then minus 3 would be negative 3. If I put in 0, 4 times 0 is 0, and 0 plus 1 is 1, and 1 minus 3 would be negative 2. If I plug in 1, I get 4 times 1, which is 4, plus 1 is 5, and 5 minus 3 is 2. If I plug in negative 1, I get negative 4 plus 1, which is negative 3, and negative 3, oops, that would become positive 3, and then 3 minus 3 would be 0. And then if I plug in negative 2, I get negative 8 plus 1, which is negative 7. Absolute value of negative 7 is 7 minus 3 is 4. Are those the same points y'all got? Okay, so let's see what it looks like. Negative 1/4, so negative 1/4 about right here, and it goes down to negative 3. Zero, negative 2, and 1, 2. That's way up here. So it looks like this side of my graph is going to do something like that. And then the other side, I go negative 1, 0, and then negative 2 way up to 4. Like that. Remember, if you start out at a point that's not an exact value, that's a fraction, that's not an integer, it's going to make your graph look like it's off, but it's really not. How about the domain here? Oh, you didn't have, oh, that's right. Oh, we got a shade. I'm sorry. I should have dashed that, right? Because it's less than, not less than or equal to, so this is actually dashed. And then I got to decide where to shade. So it's y is less than, and less than is going to be outside here. Anything else on your homework? What? Yeah. Number 6. This is the piecewise. Is that the one you're talking about? F of x equals, I'm going negative 1 if x is less than or equal to negative 6. Negative x minus 4 if x is between negative 6 and 0. And absolute value of 2x minus 5 if x is greater than 0. The first one's just a horizontal line, and I hope at this point you've done enough of these that you really don't even need to plug in here. But if you do, it's negative 6, negative 1, and then smaller than negative 6, so maybe negative 7. 1, 2, 3, 4, 5, 6, 7. The closed dot going in this direction, horizontal line. Then we've got the line negative x minus 4, so I'm going to plug in negative 6, and I get negative 10. And I plug in 0, and I get negative 4. This one's going to be an open dot. This one's going to be a closed dot because of these signs here. So -6. We'll call this -6, -10. And then up to 0, -4. Closed. Now the last one's the absolute value, and that's the hard part of this one. The first thing I want to do is see where my vertex is, right? Because that's going to determine if I need, how many points I need. So the vertex here, 2x minus 5 equals 0, so 2x equals 5. X equals 2.5. That's bigger than 0. Do you agree? Is it bigger than 0? Yes. So it's going to include my vertex. So if you think about what an absolute value looks like, it looks like this. But I'm going to be cutting it off somewhere like this. So I'm going to plug into 0 to start with. And whenever I plug in 0, I get 5. Then I'm going to do the vertex. The vertex happens at 2.5. And what's the other part of the vertex? 0. But now I need one more point, because what's happening, this is 0, 5, and it's open. 2.5, so 1, 2, 2.5, 0. There's the vertex. But I need all the rest of this graph on the other side, right? It doesn't keep going down. That's the point where it flips up. Yeah. Say again? Put that one what? Oh, I sure did. Thank you. Sorry. But this is where it flips, right? So it's going to keep going, but it's not going to keep going this way. It's going to keep going that way. So I need one point on that other side to know that direction. So for this one, maybe I also pick 3. I don't know. It doesn't matter as long as it's on the other side. So I can connect it and keep it going in that direction. So if I put in 3, 2 times 3 is 6, minus 5 is 0. And then it keeps going that way forever. Does that make sense? See how I included that vertex in there? Now, if it was cut off here and it was going that way, I wouldn't have to worry anything about the vertex. How about domain? Did you have to do that here? Yeah. Yep. What about the range? The lowest the graph ever goes. -10. Open or closed? Open. Up to what? Does it go up to infinity? I start here and I start going up, 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 but look, this ends. See that? Doesn't pick back up until -1. So it goes up to -4. It stops with a bracket, and then it picks back up. Yes, ma'am. What? Oh, I did it wrong. It'd be 6.2. I see what you're saying. Sorry. This is up here. So this piece goes like that. Why didn't y'all tell me when I graphed it? There you go. Sorry. When you plug -6 in here, a negative times a negative is a positive. So you get +6 minus 4, which is 2. Now what's the range? The bottom is, what's that point? -4 up to what? Right? What's the lowest the graph ever goes? -4. Then it goes up to what? Does it? This point, what is this point? This point is 6.2. Where is 6, 2? 6, 2 is actually a little further. If this is 0, 5, let me put this up so you can see a little better. It looks to me like 5, well, but 5 is there. 6, yep, up to infinity. You're right. Up to infinity. If there is a vertex, and the vertex is in this range of numbers, then you need to include it. You need to go on both sides of it there. You can. It doesn't happen often, but it just depends on where you cut it off. So for this one, it might make more sense if you did like the eraser method where you drew it and then erased what didn't apply. And if you did that, you'd see that you just cut off everything from here and you just erase that side of it. Anything else? Everybody good? All right, so here's the deal. You have a packet in front of you with parent functions, and there are a lot of parent functions. We are not going to get to all of them just yet. We're going to not even do the last 3 today. The ones we will mainly be working with transformations right now are just going to be the first 3. We will get to more, but I really need to introduce you to the parent ones first. So we're going to do the parent functions and some analysis, which is over there, and that very well could be all we get through today. I don't want to throw too much on you in one day, but the last 3, don't X them out, but we're not doing them today. So when it starts on the back page, reciprocal, exponential, and logarithmic, we will not be doing those today or in this unit either. Those will be future units. But I don't care to even get into the parent functions with you right now because I think it'll just make it too difficult. But let's go through. So what is a parent function? And there's a couple of things in the analysis over there on the right-hand side that I'm going to have to stop on this first one and explain to you what it means. But hopefully that will clear things up as we go through the rest. So the first one will take us a little bit longer to get through than the rest of them will. It's a very real possibility you may not have homework tonight. It depends on how much we get through. We'll see. All right, so the first one is linear. Okay, and well, let me go back. What is a parent function? So if you look up at the top, it is, yeah. Parent functions are defined for you there. They're a family of graphs that share similar characteristics, and the parent function is the most basic of those. So before any type of transformations, which we will talk about, are done to the function, that's what we call a parent function. So we have these different types, and we have talked a lot. You should be very familiar with the first few. But let's talk about linear first. So a linear function, the parent graph, and this will go in the little box right under it. What does the parent function look like? Well, it's just f of x equals x. That is the parent function for a linear function. So graphically, this should be an easy one for you to graph. What does it look like? It's not a trick question, y'all. It looks like a point, right? It goes through 0, 0, a slope of 1. So that's the line y equals x. Do we all agree? Okay, so let's talk about some, it says characteristics, I call it analysis over on the right. What is, and this is just of the parent function, so just the function y equals x, what is the domain? Negative infinity to infinity. Bless you. How about the range? The same thing, it's negative infinity. This is your most basic parent function if it's y equals x. Look at just this line, just this one. What is the x-intercept? In other words, where does it cross the x-axis? At 0. So the x-intercept is x equals 0. How about the y-intercept? It's 0 also. Then it says the maximum number of roots or zeros. Now, what is a root or a 0? What does that mean? It crosses the x-axis. So if I stretch this, shrink it, turn it, twist it, move it up, down, left, right, how many times could it ever possibly cross the x-axis? Once. It's never going to cross more than once. Do you see that? Does that make sense? No matter how I move that line, I don't know if it'll let me do this. Don't let me do what I want. Okay, well, no matter which way I move that line or how I change the slope of that line, it's never going to cross more than once. So the maximum number of roots are 1. Now here's where I need to stop just a second and explain to you what end behavior is. So I'm going to come off to the side here. You need to write this somewhere on your paper or in your notes, wherever you want to. End behavior describes the ends of the graph. Ends of the graph. How many ends does my graph have? 2. Does everybody agree? Here's one, and here's one. Now the notation is what's really funny about end behavior. So here's the way they're always set up. Because there's 2 ends, I'll have 2 mathematical sentences, okay? I'll say as x, and then I have this little arrow, and this little arrow means approaches. Approaches just means gets really close to, okay? As x approaches infinity. Now, if I'm talking about x approaching infinity, I'm talking about x getting really, really big, right? Which end of the graph do you think I'm talking about if I'm talking about x getting really, really big? I've got 2 ends circled. Which end do you think I'm talking about? The top end. Why? That's the direction x gets really, really big, right? Here x might be 10, but over here x might be 1,000. It gets really, really big that way, right? So this means anytime you see as x approaches positive infinity, this means the right end of the graph. Okay? So I start out as x approaches positive infinity. Then it says f of x, and f of x is the same thing as what? Y. That's right. Y approaches, so now I'm talking about y. So instead of left or right, I'm talking about up or down. What do you think this approaches? What does y do? If I'm looking at the right side of the graph, it's increasing, right? Look, the right side of the graph is going up. This literally says the right side is going up. But this is the mathematical sentence for saying that. As x approaches infinity, f of x approaches infinity. But there are 2 ends, and that's just one end. That's the right side. What do you think the other side looks like? As x approaches, and let me get it here. Negative infinity. F of x, or y, approaches what? Negative infinity. Because the left side, this is the left side, is going down. So if you need a little cheat sheet, x approaches means right. X approaches negative means left. F of x positive means up. And f of x negative means down. So, welcome. I know this is tough because this is new. This is new notation, completely new on the analysis part of it too. When we get done with analysis and everything, you'll learn about analysis. You'll have like I think it's a 10 or either 11-step analysis for every function you do. So we're just getting started in our analysis portion here. The last thing says continuous or discontinuous, and this is just something that you circle if it's continuous or not. So continuous, and we're just brushing the surface right now. All of these things we will go into a lot deeper and in more detail as we move forward. But continuous basically means, in layman's terms, you can draw it without picking up your pencil. That's what it means to be continuous. If you can draw that graph and never have to lift your pencil off the paper, it's continuous. If you have to lift it up to draw another portion of it, it's discontinuous. Can you think of one that we've done that is discontinuous? The step function. Somebody says step. Well, absolute would actually be considered continuous because I could do it. But a piecewise would be discontinuous. You see the difference? Connected would be continuous. Disconnected would be discontinuous, if that helps. So a linear function would be what? Continuous or discontinuous? Continuous. That's exactly right. Everybody good so far? Let's go to the next one, absolute value. This is kind of a boring day, and I'm sorry, because we are just defining parent functions here. You've done absolute value. What do you think the parent function looks like for absolute value? In other words, the equation. There's nothing else there. It's just the absolute value of x, and that's it. That's the parent function. So if I graph this, by the way, when you start pre-cal, you start out with like 12 parent functions that you have to know backwards, forwards, left, and right with all the analysis. So this is getting you set up for that. Absolute value. Where's the vertex? In the middle, right? We set this equal to 0. 2 up, 2 down. This is easy because it's just absolute value of x. So I can do, if you want to do a t-chart, by all means do a t-chart. This is getting us, what we're going to do with these parent functions is it's going to allow us to do some complicated graphing without doing t-charts. But I have 0, 0. I'm going to go 2 up and 2 down. There's my parent graph. So parent function, parent graph in green there. Give y'all a second to catch up with me. What's the domain? Good job. How about the range? Oh, 0. Is the 0 a bracket or a parenthesis? A bracket, because that vertex sits on that origin. Looking at just the parent function here, what is the x-intercept? How about the y-intercept? Now I've got that pesky little question, the maximum number of roots or zeros. What do you think that is? How many times if I 2, why? That's exactly right. If this started moving around, right, as we have seen them do, how many times could it possibly cross? 2 times. It'll never cross more than 2. 2 is the most it'll ever cross, but it could, depending on how I move it, it could cross up to 2 times. So the maximum number of roots that an absolute value function can have is 2. Now the end behavior. So you've got it started there for you. as x approaches infinity. So I'm looking at which side? The right. What does the graph do? It goes up. So what would f of x approach? Does that make sense? The right side goes up. How about the left side? It also goes up. It's positive. Both ends go up. Yep. Yeah. Oh, yeah, you guys go ahead and go whenever you need to. That's fine. Whenever you need to go. Yes. Continuous, discontinuous. Continuous. Can you draw this whole thing without lifting your pencil? So it's continuous. Uh-huh. That's right. That's right. All right, quadratic. Now what I'm probably going to do is I'm going to switch over and just get the graph set up for you and let you go back and do the analysis portion of it, and then we'll go over it tomorrow. Quadratic, what do you think the quadratic parent function looks like? F of x equals what? You had to think of the most basic quadratic you could. That's exactly what I would do. Just x squared. The most basic of any quadratic, just x squared. So what does that look like when you graph it? Now I got to think back to how I graph a quadratic, right? First thing I do is find that vertex, which was opposite b over 2a, but b is 0. Right? And if I plug that back in, where is my vertex? I hope you're starting to see a pattern with some of these parent graphs. I need an easy point. 1, I would definitely choose 1. And if I choose 1, 1 squared is 1, right? And then I reflect and connect. You know, if you wanted to put another one on here, 2, 4, you could. You don't have to put that many points, but if you want to, just so you can see that parent graph nicely. All right, let's look at the cubic next. What does cubic mean? What does it mean if you cube a number? A third power. So for this one, the parent function is x to the third. It looks a lot different than a quadratic function. And we will talk about these polynomials in depth later. Again, I just want you to be familiar with what the parent looks like right now because we will be using these parent functions to do some transformations. This one has a middle point. If I plug in 0, what do you get for y? You get 0. So it's got the point 0, 0 in it. Now if I go 1 up and 1 down from 0. So if I let x be 1, what does y become? 1. And if I let x be -1, what does y become? -1. So what's going to happen, and it's going to get really big really fast, right? If I plug in 2 to the third is 8, right? And -2 to the third is -8. So it's going to go up really fast. So it's got this slight curve to it right here, and then it starts shooting up very fast. And it's going to do the same on this side, and it's going to shoot down really fast. Have y'all seen a cubic before? Not done one, but you've seen one. Again, I'm going to leave that analysis for you to work on, and I'm just going to, because I think you should be able to get that given the graph. This one is continuous still, because I could still, if you can trace it with your pencil without ever lifting up, it's continuous. 2 more to go. And then I'll give you time to finish your analysis. Again, we're not doing these last 3 on here. We will eventually, but we're not doing it today. Square root. F of x equals the square root of x. That's it. That is the parent function. Remember, it's the most basic one you could think of. Square root of x. Now, we have to remember something with square roots. What can we not have under the square root? A negative number, right? All right, so if I think about on my graph, could I have 0 under there? Sure. If x is 0, what is y? 0. But I can't have, if x equals -1, that doesn't work, right? Because I'd be in imaginary land, and I don't want to be in imaginary land right now. Just want real numbers. So what's a good one maybe I could plug in here? I hear 4. What's the square root of 4? 2. 1, 2, 3, 4. 1, 2. Y'all picked 4. I probably would have picked 1. Nope, but that's okay, because that helps you to see the pattern a little bit better, so that you're not, you see that it's not just a line, right? When I've got 3 points on there, I can tell it's not just a line. I might, if I only had 1, 1, I might be inclined to do something like that, but that's not in fact what the graph is doing at all. The graph is starting here. It can't go beyond that because it can't be negative, and it makes this kind of curve this way. Cube root is a little bit harder. You probably haven't seen cube root yet. We have not gotten to cube root, but again, I just want to show you the basics of the parent function. Do you remember whenever we talked about square roots and I told you there was a little imaginary 2 that sat right here? Because that's saying what number times itself twice gives you what's under the radical, right? Well, we can change that little teeny number to anything we want it to be. And in the case of cube roots, we change it to a 3. Be careful when you write it. The 3 has to be itty bitty and sitting in the radical. Otherwise, it starts to look like 3 times the square root, which is not the same. So this is asking me what number times itself 3 times gives you what's under the radical. Okay, so if I ask you what's the cubed root of 8, what times what gives you 8? You see what a cubed root is doing there? You don't understand it completely just yet. It is okay. We will get to a whole unit on roots. No, go ahead. Well, no, because it's 3 times 3 times 3 would be 81. So the cube root of 81 would be, 27. The cube root of 27, sorry. The fourth root of 81 would be 3. Look at all those roots. But just so you know, so just for this one, I'm just going to have you do, we know the 0, right? If x is 0, what's the cubed root of 0? 0. This one is different than a square root because remember with a square root I had to stay positive? I don't have to do that with a cubed root. Do you see why? What's the cubed root of -8? -2. I can have a negative under there when it's a cubed root because a negative times a negative times a negative would give me a negative back out, right? I can't do that with square roots because anything times itself gives you a positive value. Cubed roots, I can take on the negative. So, if x is 1, what do you think y is? 1. Cube root of 1 is 1. 1 times 1 times 1 is 1. What if x is -1? You don't have to put any more points on it than that. I'm just going to show you the shape of it. It kind of looks like a square root graph, but then another piece of it as well. Almost looks like a cubic on its side, which it is. If you had rotated that cubic graph around, that's what it would look like. I am going to stop there, let you fill out the analysis portion, and then we'll talk about them, and we will get to the transformations tomorrow.